Everyone to our webinar here today. My name is Arya Hakimian. I'm an application scientist at C-Therm. And today we're taking a look at method selection for thermal conductivity testing. Today's webinar will be focused on a variety of methods in the field of thermal conductivity testing. We'll take a look at, some of the pros, some of the cons, where they're commonly employed, and some testing considerations that you should be aware of in deciding which is going to be the most appropriate option for what you're looking to do. So we'll start out just very quickly with a little background here for those that are new to C-Therm, who we are, what we do. So C-Therm, we are focused on the measurement of thermal conductivity, specifically through the advancement of the transient class of measurement technique. Really, our goal is to simplify thermal conductivity testing for the materials of tomorrow. And in today's content, there will be, of course, some examples and data featuring specifically on the transient methods, as well as options like the steady state options that exist out there as well. But from the transient side at C-Therm, the main focus will be on the options that are available on our Trident platform. So Trident was developed as a modular system, bringing together 4 of the most prominent methods in the transient space. Amongst these different methods, of course, they all, again, as with all methods, will have their pros and cons, certain considerations to keep in mind. So we'll be going into detail on these here today as well. But the idea behind Trident, really something we like to speak about is, when you are looking at methods, and kind of the quote here, when all you have is a hammer, everything looks like a nail. The idea holds that if you are trying to force a test on using a specific method that exists, there are certainly scenarios that we will run into where it's going to result in some non-idealities. So when you're approaching the measurement of thermal conductivity, it's really good to have a flexible approach in terms of picking the tool that is really most appropriate for the task at hand. A lot of the content featured in today's webinar is also available in a written form in our method selection guide for thermal conductivity. For those who have not taken a look at this, this is a great free resource to take advantage of. It really gives a lot of background on some of what will be featured here today, but also some additional pointers, different FAQs on some of the different methods that exist out there. And details of that sort. So if you haven't already checked this out, would certainly recommend taking a look. Okay, well, let's start from the beginning. What is thermal conductivity? So in essence here, when we're describing thermal conductivity, we can essentially describe it as the fact that this is a material's ability to transfer heat or conduct thermal energy. It's an intrinsic material property of the sample in question. When we're looking at really all the results and different data sets in today's content, everything will be in the units of watts per meter Kelvin. There are other units and conversions between the watts per meter Kelvin, the imperial options as well. Another property that we'll maybe touch on a little bit is R value or thermal resistance. Some of these related properties, thermal diffusivity and effusivity as well. So I did want to highlight, amongst the main considerations, thermal conductivity is certainly going to be the main focus. Thermal diffusivity and effusivity are 2 other related thermal properties that are also quite commonly referenced and are of interest depending on the application space. Just wanted to quickly put them up here, very brief definition, but also just showing the relationship between effusivity, diffusivity, and thermal conductivity. And the main thing we can highlight here is that they are related through the density and specific heat. Now, again, when we're looking at a variety of methods today, going to classify them really into 2 groups. The more traditional steady state methods, these would be things like your guarded hot plate, heat flow meter, TIM tester style setup. These are like the steady state class. And then there's transient. So again, transient is what we focus on here on the Trident platform, but there are also methods like, laser flash, 3 omega. There are other methods that we will also be covering in today's content. And again, kind of going through these one by one here together. So to start out, steady state. We'll start with steady state. By and large, steady state it has been around longer. It is an older method approach for testing, but I wanted to give some just general kind of ideas and principles behind the method. So in a steady state system, we are looking at the heat flux between that is applied to the sample. So the resulting temperature difference is being monitored and recorded within the system. This is your classic case of calculating thermal conductivity based on Fourier's law of heat conduction. Now, when we talk about steady state, what that essentially means is that the material under the conditions of the test is not changing as a function of time. So as the measurement will initiate, there's going to be some variation in the temperature between the material, but over time it will enter into this constant zone. And this is where a steady state measurement is essentially taken. In steady state, these systems by design are more like from a data processing standpoint, are a little more straightforward, simpler calculations. Again, they're an older approach, more traditional way of measuring thermal properties. But just because they're older doesn't mean they are not used. They are certainly used in a variety of different areas. One of the most common ones that I generally will encounter in talking with a lot of different folks in a variety of industries is heat flow meters and guarded hot plates. These are your classic dual-sided plate design setup where the sample is placed in between, again, measuring the heat flow through the material. And there's some things to keep in mind here. Heat flow meters, guarded hot plates, sometimes referenced by the ASTM standard, so ASTM C518, C177. By and large, in the insulation industry, they are viewed as a golden standard, especially when it comes to product certification testing. It is something that is just very well ingrained in that industry. Really good for lower conductivity. There are certain heat flow meter style setups that push this upper range a little bit, but generally, if you kind of look across the board, most commonly referenced for samples below 1 watt per meter Kelvin. Really good at measuring across the full thickness of a material. This is one of the inherent benefits of a steady state and specifically heat flow meter style setup is it's capable of testing through the full thickness. You can also look at testing multi-layered materials. They've got some nice advantages going for them here. But there are certain things to flag. Again, I really mentioned that these are designed most commonly for like insulative testing. So things like your batted or foamed insulation, foam boards, whatever that may be. And again, commonly referenced on technical data sheets for this for insulation. So you can see C518. Now they're putting this in terms of R value, but R value is just the thickness of the material over conductivity. But again, using the C518 method to get at that type of data. Now, that being said, there are certain considerations to be aware of here. One of them is that steady state in general will have a much longer test time. So this is true across the board. They're typically hours, some systems, and depending on the conditions, can even be days. One of the reasons behind this is, again, you're waiting for that steady state condition to be met. So it does inherently require a longer duration. And if you are looking to conform strictly to the C518 standard, there are certain requirements in there that must be met in terms of, measurement consistency and stability, modified testing procedures are certainly employed. Many many cases. But if one of the main advantages of using a steady state or heat flow meter, for example, is to, conform to the C518 standard, well, again, you're going to want to make sure you're checking all those boxes there. So longer in duration. One of the other big ones, especially for groups working in an R&D environment, is that they do carry some stricter sample geometries, in the sense that your dual-sided plate design, typical sizes, 30 by 30 centimeters, or about a foot by a foot. The thickness ranging, typically in the centimeter range. But, there are many groups that are producing samples that are just very small, especially, again, early R&D stages where you're not able to produce at the volume or the size that is typically used for these more traditional methods. There can be certain challenges there on that front. As I was saying, not really designed for high K. It's essentially when you're getting those very high levels of heat flux, you're not able to maintain that stable temperature gradient. This is where you'll start to get some bias introduced, and just again, simply where the performance range isn't really designed for. And as I said, one of the benefits, of course, is measuring through the full thickness. And while that in one context is quite advantageous, what you lose out in a device that measures across like a larger area, kind of averages everything out, is if you're experiencing consistency issues. Again, maybe that's across the surface, from side to side. Those types of issues aren't as really detectable with these more traditional approaches. We'll talk about how we can address those with some transient options here. But again, each one of these will have their pros and cons to be aware of. The next one I wanted to talk about is the TIM tester. So again, another one that's very commonly referenced in this case, of course, for the D5470 compliance. Very commonly used for, of course, thermal interface materials, or TIMs. It is a TIM tester, for your gap pads, thermal paste, grease, adhesives, whatever those may be. So for a TIM tester, again, some really nice advantages there, specifically with that standard. One of the really commonly requested, I'll say, like additional properties for measurement is thermal contact resistance. The TIM tester is a great option in measuring that. When we're going to talk about some of the transient measurements, contact resistance is something we actually have to overcome to be able to take the measurement. So if you're looking for a specific way of quantifying contact resistance, a TIM tester is going to be really great for that. Also, things like bond line thickness measurements, there are certain, like, really, I'd say very TIM or electronic industry thermal management focused outcomes that the TIM tester can certainly provide quite well. Now, with the TIM tester, again, some considerations to keep in mind. In this standard, it describes it as apparent thermal conductivity, but it's really thermal conductivity is being determined here from the impedance measurement. And because of that, it is sensitive to the thickness reading and the applied force in those, again, the double-sided setup there. So something to keep in mind there as you're kind of setting up your device for measurement. You'll want to be very, cautious on that front. Again, like I said, with any steady state, really, it's not able to really pick up on those side-to-side differences in a very straightforward way. You're getting that average value across the entire sample. And again, in many contexts, that can be quite a very good way of measuring. But if consistency is something that you're really trying to hone in on, there are some alternative options that we'll talk about. But all that being said, for groups looking at TIM testers, and I kind of mentioned this thickness reading and applied force being a limitation. There's a group, ZFW, that we've looked into their TIM tester, and something that we are going to be using here. It is a very good option because it really helps mitigate some of the more traditional issues with some TIM testers that exist on the market. They have a high resolution optical system. It doesn't rely on like the pure mechanical measurement. So you get a much higher accuracy on the thickness reading that is done. It's a really interesting setup that they use there. You can apply constant and variable pressures. So you can do some really interesting things like simulate thermally induced gap changes. They have delamination testing capabilities, capable of in-plane thermal conductivity analysis as well. So, for those that are looking at a TIM tester, this is certainly one of the stronger options on the market here today. Now, so, talked a little bit about steady state. Going to pivot here into some of the transient methods. So again, going to kind of go through some recapping of just some general pointers behind transient. This is, depending on the specific method involved, is a little bit generalized here, but the idea is that your sensor is placed in contact with the material of interest, with your sample, and it's electrically heated. So this is providing a pulse or a burst where the heat is being monitored as a function of time. So again, yes, this is being recorded. And then the rate of change, again, similar is being observed here, but being transient, again, the big differentiator here is that we are doing the analysis in this region earlier on. So this is before you reach that kind of consistent, constant, steady state point. So transient implies that temperature is changing as a function of time. It is not constant there. Data processing does involve more complex mathematical analysis. So if you do look into some of the math behind some of these transient approaches, they're certainly a little bit more involved. But again, some of the benefits that we will highlight here, specifically on transient, is the ability to test under some more interesting representative testing conditions. The sensors, they can be very easily placed in these different environments. So unlike your more traditional steady state devices, which are quite large, these sensors are very small. So you can put them in environments that are representing an application of interest. Again, the big one for many groups is that they're much faster. Again, because we don't have to wait for that steady state to be reached, most transient methods will have test times on that seconds to minutes time scale versus hours to days. So there's certainly some throughput capabilities that are very attuned to the transient class of measurement. And overall, again, depending on which method you're looking at, but there's generally more flexibility, not only on the size of the sample, but what type of material can we test. Everything ranging from solids to liquids, powders, pastes. There are certainly a variety of options here to investigate in the transient space. So I wanted to start out with really the four methods, the four transient options that are available on Trident, and walk you through some of, again, where they're commonly employed, what are their advantages, and also what considerations you should keep in mind when looking into these options. So the first one here is the modified transient plane source, or MTPS. So the MTPS here, this is a single-sided sensor design. It's actually a patented device, so this is available solely through C-Therm. The MTPS active area, something I always like to point out for groups, is that it's about 18 millimeters in diameter. So when you're considering like what size sample do I need to produce to be able to take a measurement here, as long as we can cover the surface of that sensor, they're about the size of a quarter. So again, quite a stark contrast here, starting out with MTPS compared to, the sizes that were typically needed for, let's say, like a heat flow meter, which were, again, many centimeters wide. Now, in terms of the thickness requirement, just very quickly going through here, you can see it ranges. It does vary depending on the type of material and the conductivity range that you're in. Generally speaking, though, with the exception of very conductive metal samples, which do carry a stricter sample size format, it is quite flexible. As long as these minimum thicknesses are met, there is no maximum size limitation. It is quite flexible on that side. So again, everything from insulation, aerogels, polymers, ceramics, and of course metals. But it is also capable of doing testing of non-solids. So with the MTPS, it's very simply a liquids and powder cell. It's a metal fitting, that just fits right over top of the sensor. Allows you to be filled up with whether it's the paste, the powder, the liquid, whatever that may be. And overall, only requires a very small volume. Again, there's been some groups that we've worked with where, again, R&D materials, you're only able to produce maybe 5 or 10 milliliters at a time, if that. If those constraints exist in your research and you're looking for a way to be able to test something, well, again, the MTPS does provide some nice options there from that side of things. And I wanted to share one example here, like one highlight of the MTPS, where we see it commonly used, like what are some of the really biggest advantages. And the one I picked here, and something we talked about in a variety of different areas over the years, but it's thermal mapping. This is still, by and large, I would say, one of the biggest challenges groups are facing in their material optimization is the consistency. And like I said, with the steady state methods, very good at what they do, but you're getting that averaged out overall value of the material. How do you go about getting a representative understanding of the consistency? So MTPS is the solution for this. The idea here is if we had a sample, and again, this is by all accounts, a very exaggerated poor sample, but to illustrate the idea here, how do we quantify how inconsistent it is, and to what degree is that impacting the thermal conductivity of the material? So with the MTPS, we can take the sensor, again, it's single-sided. You can place it at these discrete locations. So this is just basically moving the sensor around, putting at different spots across your material, and then very quickly taking a measurement. Each one of these data points, start to finish, is about 60 seconds or so. So with under 10 minutes, if you had a piece of material that you wanted to do a quick consistency check on, you can do that in minutes. And this example here is looking at the filler consistency within a polymer. We've done some work with groups that are looking at consistency of coatings on a material, like variations in density within the sample, how those different factors are impacting those localized consistency considerations. It is something that can be quite important to look at, especially, say very importantly for like thermal management solutions where you need that very consistent and uniform heat transfer, or else you'll introduce some potential safety risks there. And ultimately, with a test like this, what it really helps with is that iteration velocity. It allows researchers to tweak your formulation, see what's going on, and then from a consistency standpoint, give you that confidence that yes, the material, regardless of where it's sampled from, which batch is coming out, it is giving me my consistent same performance each and every time. Now, with the MTPS, of course, as with all methods, there are considerations. So there's two really important ones that I typically will address to folks. And one is the fact that the MTPS is a calibrated method. And what this calibration really allows for is a very simple and easy approach to testing. In terms of the methods available on Trident, it is going to be the fastest and easiest one to get set up and running with. But each one of these calibrations comes with a specified performance range. There are factors built into these around the density, the heat capacity, etc. But overall, as long as you're aware that the different calibrations exist to accommodate different ranges, you'll be able to source one that will, again, match your material of interest. And actually, even within the Trident software, for groups that, again, if maybe you have an MTPS and you're using it, if you've ever put a material that is just simply not within the calibration range on the sensor and ran it, the software flags that for you. So there's never this issue about wondering like, is that sample actually within the calibration range or not? You'll get that flagged visually from the thermal conductivity value. The other point though here with MTPS, the test times are very short. They're about 1 to 3 seconds in duration. So that heat pulse is very, very quick. And to allow for that efficient heat transfer into the material, we use a contact agent. Now, this is really only used for testing of polymers, ceramics, and metals, but the challenge can be is if you're testing something that is potentially hygroscopic or, potentially it's a conductive but yet porous substrate material, that can cause some compatibility considerations, right? And actually, the next method we're going to talk about, which is the more traditional TPS, is actually how you would address or get around some of those potential challenges. So jumping into it, the TPS, like I said, this is another method that is available on Trident. The TPS, or transient plane source, you can see the sensor design, very different from the MTPS that we just showed. It's actually a very thin, flexible, double-sided sensor, available in different sizes, as you can see here. And when we talk about TPS, it's really important to define the fact that there are different utilities. You can view these as different modules that are available with TPS. And the bulk utility, this is your standard form, most basic form of TPS testing, really geared towards isotropic materials. The result gives you this average value of the geometrical average of essentially the in and through plane. So again, really geared towards isotropic. But the thing I'll flag here is that with the TPS method, the sample size requirements aren't based on anything to do necessarily with the material type or the conductivity range. Rather, it's based on the size of the sensor that is used. So you can see there's just a fixed scaling recommendation. So your diameter of your material should be 2.5 times the diameter of the sensor that you use, with a thickness scaling 1:1. And again, this is a double-sided sensor. So you're placing two samples each time, one on the top, one on the bottom, to create that stack. Now, the TPS, it conforms to the ISO standard, which is, again, one of the, I'd say, a main reason some groups will gravitate towards this, but also for the access to some of these more advanced utilities. Things like slab, anisotropy, thin films capabilities. These are all unique options on the TPS. Again, the ISO standard does provide some definition around, certain, requirements for these methods, and what differentiates the measurement from the more traditional bulk approach. But effectively here, what this opens up the door for is sample formats that would not meet the thickness or dimensional requirements of some more traditional methods, or even like the more traditional bulk mode of analysis. And one of the biggest examples of this is testing thin, high K materials. This is often a challenge because, generally speaking, when you're dealing with a conductive material, like I showed with the MTPS and the size requirements, for example, you needed a thicker piece. But what happens if you're limited and you only have a very, very thin piece of material? Maybe it's a thin film format or like a sheet, but it's expected to be high K. Well, the TPS slab utility is really great for these specific samples. And I wanted to share this one here because you hear a lot about exceptionally high K materials, graphite, carbon-based materials, but often those are achievable when it is, again, in a thinner format. And some test data we have here on pyrolytic graphite foils ranging from 12 to 100 microns, we can see getting actual measured results just shy of 1800 watts per meter Kelvin. So a sample like this, like a foil, a pyrolytic graphite foil, it's one that really does require a specialized testing setup. And in this case here, that's the TPS slab feature. Now, again, with TPS, certain things to keep in mind. Like I said, it's a double-sided sensor, right? So in the standard operation, according to ISO 22007-2, it will need two identical samples. They do have some fairly strict wording in the ISO around this. Now, of course, there are certain, if your samples are a piece of copper and a polymer, those are two very different. You're not going to get a great outcome there. But as consistent and uniform as possible between the top and bottom. And actually, there are many groups that we work with that will actually use the MTPS to do that mapping and consistency check before they actually do the TPS measurements. Because again, you're going into a measurement like this with the confidence that your sample is in fact optimized and consistent in the top and bottom piece. With TPS though, the the other big difference between MTPS is that there are no predefined calibrations to pick from. So you as the operator are in more, you're in the driver's seat, you have more control over your test parameter design. The analysis that is done within the data that's collected is also run by the operator. It's more complex in that context. But what it opens the door for is, again, groups that are, maybe you're dealing with highly novel materials, maybe trying to pick a specific calibration isn't one that's really as viable for you, and you want to have full control over your measurement design. Well, this is something that is offered on the TPS. And there is a very well-defined SOP on how do I ensure measurement, the results that I'm getting are even valid. Well, there's a series of checks. Again, these are all outlined in the ISO standard. But these have actually been integrated into the Trident platform software. So you'll have full coverage and kind of knowing that the results that you're getting are in fact meeting the requirements. And if they're not, what adjustments do you need to make in order to get them there? The last point I'll flag is they're really the TPS, for all its benefits for a variety of solids, it's not one that is very ideal for liquids. There's a few reasons for this. If you read through the ISO document, the 17, 18 pages, however many it is, I think there's a total of 1 or 2 sentences on recommendations for liquids because it's just really not geared towards that type of testing. Convection, introducing convection and difficulty maintaining that planar probe alignment. Like I said, it's a flexible sensor. So, very good for solids, not one that we see as commonly used for liquids. I did also want to flag, and again, this is a question we get sometimes, is, what's the difference between TPS from the TC kit and on Trident? So if you're familiar, we do have a TC kit option that is essentially a TPS system, but it is very much an entry level basically package here. It doesn't come with a predefined controller. It connects to like a Keithley SMU. It's also much more limited in its capabilities. But for groups that are looking just to get in the door on some, bulk thermal conductivity testing, ambient up to maybe 80 degrees Celsius, the TC kit is one that does unlock some nice entry-level capabilities. So just putting that out there, the big thing to flag is that it doesn't strictly conform to the ISO like the TPS on Trident does. And this is because in the ISO standard, there is some very strict requirements on the electrical design and the circuitry that's basically connecting the sensor to whatever is kind of collecting it and monitoring those signals. TC kit does not have those specific components, so very technically you would not meet that ISO. So certainly a nice option to get your foot in the door, but something to consider in terms of what do you actually need? Is the ISO something that's required? Do you need access to things like SLAB? Those would be some decision points to think about there. And then lastly here for TPS in particular, within the last couple of years, there is now a single-sided TPS option. You could call this a MTPS, like modified TPS. It is fundamentally and like physically very different from C-Therm's MTPS sensor. The single-sided TPS, it does conform to a slightly different ISO. So this is ISO 22007-7. So this is, again, a more recent release. But effectively, this is a modification of a standard TPS sensor that is essentially supported on one side with an insulative backing. Some changes in the math and how things are interpreted there, but for all accounts, the single-sided TPS is excellent for samples that, one, don't test well with a contact agent, and again, would result in some issues with C-Therm's MTPS, and two, are limited to one specimen. So if you only have one piece of material and it doesn't work well with a contact agent, TPS single-sided is certainly a good option to pursue. It does have some more limited capabilities, especially when it comes to low K. It's really best suited for more conductive materials. If you look up the specifications in the ISO, this is all well documented and kind of recommended thermal conductivity range. It also has a slightly wider accuracy than the double-sided configuration. my recommendation is where possible, double-sided will always be better in terms of the absolute performance range as well as your accuracy. But again, if you're running into some limitations there, it's a good option to look at. So moving on here. So those last two transient methods were more flat surface-based contact measurements. Next up is the TLS, or transient line source. Now, this is a needle probe style sensor. So it's still transient, but fundamentally different in its overall structure and design. The idea with TLS is that the probe is immersed or inserted down into the body of material that we're testing. Very commonly used for, there's two ASTMs for the TLS. It's ASTM D5970 and D5334. One's for geological, one's for like polymer-based testing. But the idea is, there's a standard cell that we provide, takes about 60 milliliters of material. You would insert your probe down in and then go about your testing. Now, TLS, there are a variety of different TLSs that exist on the market. But one of the really unique advantages with the ones that we have on Trident are their temperature and pressurization capabilities. And this is something that we've seen being of interest for groups that are dealing with polymer melts. These might be like additive manufacturing or injection molding applications, where we're looking to test some of these materials that can be quite sticky, tacky, maybe something that's not very easily testable with other approaches, but we still need to test it under some representative conditions. So TLS for polymer melts is something that we've done quite a bit of work on, different polymers across different temperature ranges, even in conjunction with different pressurization and temperature. If you are looking for a robust sensor that is have a very low risk of sensor damage, even in these harsher conditions, the TLS is a nice one to consider. Again, it's completely sheathed in stainless steel. So unlike some of those other sensor types, you don't have to worry about them getting as damaged as easily. So very easily to get in and out of those solutions. You can clean it with some quite aggressive solvents that may potentially damage some of the other options there. So certainly something to take a look at if you are interested in doing polymer melt testing. Now, from a testing consideration side of things, I was talking like polymer melts or like some non-solids. You can use the TLS to test solid materials. There are quite, actually, I think just this year I've seen quite a few papers doing just that. The one consideration to be aware of, though, is where it's a needle probe, you will have to be able to machine or drill a hole in the sample for testing, right? Some materials may be easier than others, but if you're able to drill into the sample, and that's something that is just, you want to use this method for, maybe it's for one of the standards, for example, it is something that can be done. Now, similarly with some of the solid material testing, and again, there's some information in this in some of the standards, but using a contact agent is something that may be recommended. Again, that idea is the contact agent going to react or absorb into the material? Is that going to bias my measurement? If so, again, potentially a different option may be required, but just something to keep in mind there. And the last one is for liquids, the viscosity of the liquid that you're testing. TLS generally has a longer test time and a higher power level than some of the other options, the MTPS for sure, and actually the next one that we're going to talk about. So very good at more viscous systems, again, like more polymer melts, but low viscosity materials are prone to a convection bias. So whenever you're talking about anything liquid or non-solid in nature, any thermal conductivity measurement system that has a prolonged high heat input to the system, you are increasing the risk of convection, and convection will bias your thermal conductivity readings, right? So the last one on Trident is the Transient Hot Wire, THW. So you can see the THW here, in a sense, a little similar to TLS in that it's not a flat surface like MTPS and TPS that are put in contact. Rather, it's along the length of the sensor here, which is the exposed platinum wire. very commonly used for testing of liquids. This is something the ASTM in which it conforms to is designed for, I believe, traditionally for engine coolants, heat transfer fluids. Certainly something that is still quite of interest for many groups. Holds about 40 milliliters of volume in the standard cell. So I know we've kind of talked about a few different volume ranges here, but MTPS is about, again, that like 2 to 3 milliliter range. TLS is around, was about 60. THW is in that middle spot, so about 40. So as I was saying, really great option for testing a variety of liquids, specifically, engine coolants, heat transfer fluids, whatever that may be. The ASTM D7896 standard is one that is certainly on many folks' radar if you are in this space. I've even seen it really become highlighted in all of the immersive cooling and AI and server data centers. They're methods that have been traditionally used for liquids are kind of really gravitating into that space here as well. So you can see some performance data on a variety of different materials, function of temperature, again, in conformance to that standard listed on screen. Now, from a testing considerations perspective, there's really one big one with the THW, and that is the fact that the platinum wire is directly exposed to the sample. So in the ASTM, it says, test method excludes fluids that react with platinum. One of the big ones is those that are electrically conductive. So it is really designed for non-electrically conductive systems. I know certain nanofluids, depending on what you're working on, if there's electrical conduction within the system, this isn't something that we strictly measure, but if it is an electrically conductive material, that can result in some bias there. So you'd want to potentially look at an alternative method in that case. Okay, so those are the 4 transient methods on Trident, but there are other transient methods that exist in industry, and I wanted to cover off those here before we wrap up here today. One of them, and this is probably a very common one that many folks know about as well, is laser flash, or LFA. So the idea with laser flash, of course, is it's a non-contact based measurement. The laser is hitting the sample and it's heating up. Or monitoring that, detecting that temperature change on the back side there, but very good at doing high temperature testing. Like LFA systems, out of all the methods, do provide some of the highest temperature range testing capabilities that exist on the market. In that context, they're very commonly used for testing of ceramics and metals. That I'd say that's really they're best suited for. You can get away with some fairly small sample dimensions as well. Most LFA systems have a standard sample holder, so you do need to get your sample configured to fit into whatever that dimension is. But oftentimes you're getting away with quite a small piece of material. So again, something that's certainly good for smaller sample formats, higher temperature testing. LFA really going to be your best option in that case. But some things to keep in mind with LFA. Based on the print and how the samples are set up and how the measurement is operated, they really do need to be very smooth and flat and optically opaque. So if you're dealing with a transparent sample, you typically need to apply a coating. So there's a little bit more sample prep involved. Excuse me. I kind of touched on this already, but that stricter sample format that does have to fit into a sample holder. So again, smaller format, but does have some stricter requirements. The biggest thing with LFA that I'll flag is that it is well documented that it can introduce errors when testing filled materials or samples that are anisotropic. There's within the ASTM standards and the best practices that are related to the core or the main ASTM for laser flash. It says when substantial non-homogeneity and anisotropy is present, the thermal diffusivity data obtained, because it is measuring thermal diffusivity, may be substantially in error. And as such, you should exert caution. Actually, they use the word extreme caution when determining related properties such as thermal conductivity. So LFA, very good for high temperature material testing. But if you are dealing with more, let's say polymer-based composites or composites in general, something to be aware of there. I've seen in many cases you get a positive bias. So you get like an exaggeratedly larger value than what's actually really going on there. Again, in any case, when your samples aren't consistent, you're going to run into issues in almost any method that you use, but certain methods will, of course, introduce a larger introduce bias in some of those cases. One here that is not as commonly referenced, but very interesting in what it can offer in terms of capabilities is the frequency and time domain thermoreflectance instruments. So again, non-contact based here, you have like a laser and optical system set up. These do involve a much more complex actual instrument setup compared to, something like the TLS, where you're just sticking the needle into a sample and taking a measurement. So there's a lot more to consider on the actual setup there. But the thermal transport properties here, these are derived based on the material's reflectance as a function of temperature. And when we look at the two different ones, frequency and then time, so frequency domain thermal reflectance, this is really a very powerful tool when testing complex structures, maybe irregular shapes, like multi-layered. It has the ability to do depth profiling. So maybe even very thin materials that are multi-layered on a substrate, whatever that may be. There's some really nice capabilities here that are opened up with this style of technique. TDTR, time domain, this is a really good option if you're looking at very conductive, very highly conductive materials, also compatible for anisotropy based testing. So both options are using this thermal reflectance basis, but one is time-based and one is frequency-based. Now, for both of them, some considerations, kind of doing these in parallel. In both cases, you may require density and heat capacity as an input to be able to quantify your thermal conductivity. So that may be something that is needed depending on the specifics of the setup and the sample that's in question. The frequency domain option does carry more complex data interpretation due to the fact that we are looking at frequency-dependent variations and their resulting effects. Whereas TDTR, the time domain, there's more complex optical alignment and also the need for like ultra-fast laser systems. So one is a little bit more complex in the analysis portion, the other is a little bit more on the actual setup. And again, these are kind of contrasting each other, where the FDTR is less effective for highly conductive samples. Again, very good at those more irregular shapes, depth profiling, things of that sort. Whereas TDTR is less effective for the lower K and depth profiling, very good at the high K end of things. So again, kind of a newer, interesting focus here with some of these frequency and time domain thermal reflectance capabilities, definitely opening the door for some very interesting material characterization. And the last one here that we're talking about is 3 omega. So this one has actually been around for a while, but in terms of its use, it's one that we've seen kind of come on and off over the years, but it does really have some benefits. But again, we'll talk about what those are and where they come up. One of the biggest considerations with 3 omega is that the electrically conductive sensor is actually deposited physically onto your sample. So we're looking at modulating current. Modulated current is supplied at some frequency, and this is how we're able to get at the thermal properties of the material. So in its use case, it can be used to test very thin, even nanometer range films, multi-layered samples, capable of anisotropic analysis. So really opens up the door for some very interesting testing options. But, in terms of getting them set up, the biggest consideration around is that sensor deposition, because you do have this more complex fabrication process requiring precise alignment, traditionally done with like a photolithography setup here. There's a lot involved just to even get that sensor in contact with the sample. And of course, once it's on there, then that sensor is on that sample for that test, and that one alone, right? Now, the data analysis also, because there's a frequency component here, there are some frequency-dependent effects that need to be understood during the data analysis. So, certain things to keep in mind there. But again, these time and frequency domain thermoreflectance and 3 omega capabilities do open up some very unique testing options, especially if those are something that is, if those types of samples have introduced a bottleneck or a limitation using some of the more commonly or traditionally available approaches. So with all of that said, I know we're coming up on time here. I'll just take a moment to say thank you for those that joined here today. Quickly going through the outro here. If you do want to kind of take a look at some additional resources on our website, there's past webinars and tech libraries for some of the papers and content that is featured. Definitely feel free to check that out. Wanted to plug an upcoming webinar. So we have a guest speaker joining us on December 2nd. So the group of Vonic joining to talk about fumed alumina and maintaining thermal conductivity of silicones while functioning as a suspension aid. So we're going to be talking a little bit about here how the consistency considerations are being looked at by some of these groups using thermal conductivity in their application space. If thermal conductivity is of interest, of course, that's what we talked about pretty much for the entirety of today's call or today's talk, but we do also work with other material characterization options, Rigaku, Metrovib, and we do have thermal analysis labs, which is our fully contracted test division here at C-Therm that offers all of the methods available on Trident, some of the steady state methods we talked about, some of the other transient methods as well. So if you're looking for someone to be able to help you with doing some measurements, it's certainly something that we're happy to support. If overall you're just looking to gain maybe some more information, whether it's for testing services or for the instrumentation that we offer, we do offer free technical consultations with one of our subject matter experts. Happy to go through your specific needs and application. If that's of interest, again, definitely feel free to reach out. We're more than happy to accommodate. And for those that maybe like what they see, you're just kind of wondering where these fall in terms of price point and what that would look like for budgeting considerations. If you're looking for a quote or anything of that sort, reach out. We'll, again, be happy to provide that. And the folks, I kind of saw some names in the attendee list. So I saw some folks definitely coming from academic groups. If you're from an academic institution, either a student or you're a professor and you're looking to potentially bring in thermal conductivity options for your lab and your research group, we do have an academic support program going. You can see some of those benefits listed on screen here. But if you are from an academic institution, definitely mention that in your outreach. We'll definitely include this in the follow-up discussions. Lastly, give us a follow on LinkedIn. If you're not already doing so, this is where we post all of the latest and greatest content, upcoming webinars, blog posts, everything is on LinkedIn first. So if you're not already following us there, please feel free to do so. All right, and that brings us to the end. So I know we have a few minutes left here. For those that are jumping off at this point, thank you very much for joining.